Okay, we're back at it, and we're going to be doing an example problem this time. And this example problem follows up on what we've learned in the last at least 2 lecture videos that we've experienced together. And this problem says, explain how the above could be distinguished in their NMR spectra, and they give me A, B, and C. All right, so let's take a look and apply what we have learned at this point as far as the number of signals and where they're located and the type of splitting now that we can talk about and bring into the discussion. So for part A, it looks like I've got chlorine here to the left, but I also have some chlorines there to the right-hand side as well. However, there's 2 here to the left, to the right, and there's 1 on the left. So these are actually different. They're not the same. So there's going to be a ding dong and a ding dong and a ding dong that's going to be here throughout the entire time. So I've got actually 3 major signals that I am seeing within this molecule. The chlorines to the right hand side, there's 2 of those. So this will probably be not A. Sorry, I made a mistake. That's probably not going to be A. This is going to be C, because that is the closest to the most electronegative atoms that are there. This one's probably going to be B, and that's because it also has an electronegative atom, not 2 of them, just 1 of them. And then this is going to be the easiest ones to flip because they're the furthest away from those electronegative areas. So A, B, and C. So here we at least know we've got 3 signals in total. All right, so we can use this maybe as some justification on how to distinguish the NMRs from each other. So let's see if this is going to help us. So for part B, again, I'll take a look at the number of signals. This one has 2 chlorines, and that one has 1 chlorine, and this one doesn't have any. So just like before, ding dong, ding dong, ding dong, we see 3 signals that are all separate there. So because of that, it's not really going to make any difference compared to the A molecule that we have, because we're still going to get 3 signals here. So I'm not going to be able to use that at first glance to determine the difference between A and B. We got to go a little bit further with these guys. All right, so let's rank them anyway. It looks like this CH3 group is the furthest away from any of those. So that's going to be for A. And then this one's probably going to be B. It's got 1 chlorine, not 2. And then because of that, this one is going to be the hardest to flip. So that's the furthest downfield or the furthest away from 0. And then finally for C, let's look at this one. So that means that this is 3 signals. So for C, if we take a look at these, it looks like we've got a signal here from the CH3 group. And then this CH2 group, ding dong, we're going to have a signal there. And then this 3rd carbon, I've got 3 chlorines on this thing, right? There's no protons at all. So because there's no protons, I can't get an NMR signal here. So there's actually only 2. And this CH3 group is the furthest away from all 3 of those electron greedy loving chlorines. So that's going to be A. And then this one's going to be B. And we actually don't have a signal at all for that one because there's no protons that are there. So this one will only have 2 signals, and that is it. So this is the first step that we can use to determine the difference between A, B, and C. C will have 2 major signals. That will be the only one that will have 2 major signals out of these 3 choices. Then we'll have to go another step further and figure out how can we tell the difference between A and B. All right, so here I'm going to draw 3 NMRs. We'll do C just to do C. And then for, let's say, the A molecule, let's kind of do this number here. And then for the B molecule, we will do that number there. And then for the C molecule, we only have 2 signals, and that is it. All right, so this is the first step in the right direction. So I've got to be able to determine the difference between A and B. You know, if I'm given these, I can easily tell which one's which. I want you to look at maybe infrared. Infrared would look at these molecules and say, you know, they all have chlorines on them. No major functional groups here. It's going to be kind of difficult and hard to determine in infrared which one's which. If I look at mass spectroscopy, they all, A and B and C, they all have the same formula weight. So therefore, they all have the same M peak. but their base peaks could be a little bit different, and that will just be the height of the base peaks or the actual value of the base peaks. So mass spec would be able to do that job for us. And then NMR is a little different. NMR is going to look at these and say, well, I don't really care about functional groups. I don't really care about mass. I only care about the way the protons are ordered up in the molecule. What is the actual structure? What is the order, and how many of them are there? So that's where NMR comes into play. So if I take a look at A, this is going to be our middle carbon. And then this will be the carbon that's on just the left-hand side, and this will be the carbon on the right-hand side. And we can talk about splitting here, right? So if I look at the splitting, well, it looks like the B one has only one neighbor, and that one neighbor has 2 kids, so 2 plus 1 is 3. So B will be a triplet here. And then if I look at the right-handed carbon, that has a proton on it. It gives me a signal. And then this is going to be a, how many kids do you got? And they're going to say 2. So 2 plus 1's 3. So that means that the C signal will also be a triplet. And then if I look at A, well, I've got 2 plus 1 is 3 on that side. And then it also has another neighbor, and it's got 1 kid. So 1 plus 1 is 2. So 3 times 2 is actually 6. It is a multiplet. So 2, 3, 4, 5, and 6. So this is going to be a multiplet. I abbreviate that with an M. This is going to be a triplet, and that's going to be a triplet as well. All right. Another step in the right direction. Now we take a look at B. Does splitting give us an idea of which one's which? Is that going to determine the difference between A and B here? Well, maybe. Let's see. So it looks like I have A and a B and a C all over again. So for the signal A, I see 1 neighbor, and that 1 neighbor has 1 kid, so 1 plus 1 is 2. I just determined the difference. In the first molecule for A, that lowest frequency signal will be a multiplet, where in the structure for B, the lowest frequency signal will be a triplet. That sounded pretty fancy, didn't it? I used some scientific terminology in order to explain the difference here. But let's keep going. Let's keep going, right? So here on the right-hand side, I've got a carbon with a hydrogen. So that's going to give me the signal that we labeled as a C. And next door is 1 neighbor that has 1 hydrogen, and that is it. So 1 plus 1 is 2. So it also looks... here, let me erase this. I got excited. So 1 plus 1 is 2, and this is a doublet. The same thing is going to happen for A. Just as in our previous kind of description with A, this is another side of difference. So for A, our C signal was a triplet, and then for B, our C signal was a doublet. So this is going to be a doublet that's here. So I'll label that one with a D. And for A, this is a triplet. So I'll label that one with a T. Now let's take a look for our signal B for B. So to the left-hand side, I've got 3 protons. So 3 plus 1 is going to be a 4. And then to the right-hand side, I've got 1 proton. So 1 plus 1 is going to be a 2. And then because I've got 2 neighbors here, they amplify each other's antics. And what it will amplify is a 4 times 2, which is 8. So 1, 2, 3, 4, 5, 6, 7, and 8. So this is a multiplet here. So just like in A, we can use this to determine the difference again with all three signals. So for the A molecule, I will have three major chemical shifts. The lowest frequency will be a multiplet, the next one will be a triplet, and the next one will be another triplet for multiplicity. For compound B, we have three major signals. Those major signals in order of lowest frequency will be a triplet, then a multiplet, and then a doublet as far as multiplicity goes. Then for C, we only have two major signals. This is A and this is B. So for the signal or chemical shift of A, we will have a 2 plus 1, which is a triplet for splitting or multiplicity. And then for the B signal, I will have a 3 plus 1, which is 4, and that is a quartet for the multiplicity. All right, so we are getting a little fancier with the terminology. We can explain these a little bit more appropriately. We don't have to use these analogies every single time, even though that helps you remember what's going on. But this is what NMR is all about. So here's another example problem. Problem number 20. And it says the HNMR of two carboxylic acids with a molecular formula of C3H5O2Cl are shown in the figure 1316. So you're only seeing one, the second one's on the other slide. And it says identify the carboxylic acids. The offset notation means that the farthest left signal has been moved to the right by the indicated amount in order to fit on the spectrum. Okay, so in other words, 9.8 ppm offset by 2.4 ppm actually has a chemical shift of 12.2. All right. So I'm looking at this NMR, and I am seeing my TMS upfield here. I see a major signal that's happening here. I'm seeing another major signal that's happening here. I'm seeing another signal that's happening here. This is at 9.8, but they're telling me it's offset by 2.4. So I need to take that 9.8, which is where it's showing up, where they've drawn it, and I need to add 2.4 because it's further that way, so they don't have to squeeze everything together. That's why they did that. So this is actually at a 12.2. Doesn't really matter right now at that moment. And then I've got this other little line that's like right there. There's a possibility of something there, maybe. I just don't know. It also looks like there could be something like right here. I'm not sure, but there's a line that's showing up. And then I also see a small little cluster that's right here as well. So are those appropriate signals? Yes or no? That's something that we're going to have to kind of think about. That's something that we're going to have to look at when we start drawing these structures and try to match them up. However, I know a little bit of information here. This one, it looks like at 4.4, 4.5 right there is enlarged. And this is a quartet. So that quartet means that there's 3 adjacent hydrogens. Maybe. Don't know until I draw the structure and see if it matches. And then here, this major one, it looks like this is about 1.8, 1.7. That is the enlarged one. There's 1.7, 1.8. And it looks like this is a doublet. And that doublet is 2 minus 1, which is 1. So maybe 1 hydrogen adjacent here. The other signals I really can't tell. I mean, they look like singles. They didn't enlarge them. They didn't tell me that they weren't. But I need to figure out if I can draw a structure that kind of matches this. Yep, yes or no. That's what we're really after. Next up, here was the second one that they're talking about. We got to kind of figure out which one's which. So 2 different ways this structure can come together. And here's the NMR for that one. So I see the 0 NMR. I see a major signal that's happening right here. And that major signal has been enlarged to give us a triplet, which means 2 adjacent hydrogens possibly. And then I see another signal that's happening here that has been enlarged. That has 3. It's a triplet, so possibly 2 adjacent hydrogens that are there. And then I see another signal here that's been offset. So this one looks like it's offset at 9.8, so they add 1.7 onto that to get the real part per million. Again, not really interested in that, but that looks like a third signal that we're going to be getting. If I look at the NMR a little closer, I also see something little bitty thing there. Is that a signal, yes or no? We're getting ready to find that out. I also probably see a little smidgy thing happening here, a little smidgy thing happening there maybe. Don't really know yet. That's something that's yet to be determined. All right, so let's see if we can figure out a structure that, or structures actually, that would make these things happy, that would make them match. That's what we need to do. All right, so if I go back to the example problem, 3 carbons, 5 hydrogens, 2 oxygens, and a chlorine. C3H5O2Cl. All right, so let's clear that out. C3H5O2 and Cl. All right. If I go back to the example problem, it says it's a carboxylic acid. All right, so it's at least giving me a place to start. So a carboxylic acid, C double bond O OH, that has to be at the molecule. We know that. Now, here's the Tracy trick. I'll look at this example problem. The H-NMR spectra of 2 carboxylic acids, it is cheating because it's telling you it's a carboxylic acid. What if I gave you an infrared and I didn't tell you it was a carboxylic acid? I just said, here's a compound that's been analyzed. You should be able to look at the infrared and you should be able to determine, oh, look, that's a carboxylic acid. I think I know what this structure is going to start out being, and I'll draw the carboxylic acid because I know that from infrared lectures. That is what you should be doing. You should be capable of doing that at this point. I told you from very day one of Orgo 1, this is going to build up on top of each other. And here's a prime example. I could also give you the mass spectrum. And I could say, here is the mass spectrum of the molecule. Make sure the formula weights are going to match. Make sure the base pair will match when the thing fragments. You should be able to use the MS and to able to answer these questions. I could give you 3 charts. Those 3 charts could be NMR, infrared, and mass spec, and I should not be able to give you anything else. I could just say, go at it, folks. Here's your 3 spectra. You should be able to draw me a molecule based on that. Just a bunch of series of lines. Infrared dips, mass spec lines, NMR data, and you should be able to put all 3 pieces of that information together into one problem and be able to draw the actual structure of what I've given you. We're building up to that, believe it or not. So, in this example problem, they cheated. They told you carboxylic acids. All right, so here we are. There's the carboxylic acid. So it seems to me that we also have a chlorine in here as well that we're going to have to take care of. I've already taken care of 2 oxygens here, so nothing more has to happen in here. I've also taken care of 1 hydrogen, and that's it. So I've got 4 hydrogens to take care of in the structure. And what if, just what if, and 1 carbon, I've taken care of the structure. So what if I did a carbon here and a carbon there? That will take up 2. I'll just keep it simple, see if it will match up in any way, any form, any fashion. And then a chlorine group is going to have to be added on. So let's just add it on here at the very end maybe. I don't know. We'll just put it there first. And then I've got 4 hydrogens. So that's perfect. I mean, I need 2 there and I need 2 there in order for that to work. So this is one option. And folks, it's actually the only option, really. I mean, as far as the carbon chain goes, I can't really draw the carbon chain differently because there's only 2 carbons left for me to worry with. In other words, I can't have a carbon that just dangles down here because that will be an extra carbon. And if I get rid of this carbon on that side, it's still 3 carbons as the longest chain over on the left. It's just drawn kind of weirdly and it's pointed down. So that doesn't really make any sense at all. So as far as the carbon order goes, it said you've got 2 structures. We have 2 NMRs. The carbon structures are going to have to stay the same. I can't really hoodoo those in any way, any form, any fashion. They have to go that way. I can't put it on the other side because then it's not a carboxylic acid anymore. So that's the only way that those carbons can go. That's it. So it's going to make my job a little bit easier. So it looks like the only thing that can change here is the chlorine position. I can't put the chlorine to the right-hand side, and that's because the carboxylic acid has to be over there. So if I've put it to the end, well, that's great, but it said you've got 2 different structures, and this is the only way that that other structure can come into play. So I've got 3 hydrogens here on the end versus 2 hydrogens there on the end with the first way that I've drawn it. So these are 2 different structures that represent C3H5O2Cl. They kept it pretty simple. They didn't allow me to go in and make major mistakes or play trial and error a lot, because I'm really restricted on what I can do here as far as the basic structures go. So this looks like I'm going to have to match these structures to the NMR. I mean, that's what this is all about. So which one is which? So I'm first going to start with the total number of signals here. All right, so this will answer the question on if those little bitty things are actual signals or not. Okay, are these things that I need to be worried with? So for this particular carbon, look, there's no protons that are assigned to that carbon. So there's no ding-dong that's there at all. The same way with the signal down here at the bottom. There's no protons on that carbon, and because of that, there's no signal from that carbon. So now let's take a look at option number 1. So next door to that, ding dong, I see a signal, and next door to that, ding dong, I see a signal there as well. So I'm going to see 2 major signals that are going to be showing up in this particular compound. All right, so C double bond O, the CH2 is going to be a different signal, and then the next one is a CH2, which is a different signal. Down here at the bottom, I'm going to see option number 2. And then in that option number 2, there's no ding dong there. Ding dong is a signal, and ding dong is going to be a signal that's going to be located there. So I'm going to see in each one of these cases 2 major signals. That is what we would predict here, right? 2 major signals for each one. If I go back to the NMR, I see a major signal that's showing up there, and I'm seeing a major signal that's showing up here. And then this one says, well, you're also kind of seeing something over here on the way left-hand side that we've squeezed onto the chart. And then here, you're also seeing the same thing. This is a signal, major. This is a signal that's major. And then look at that funny little squiggly thing. I mean, that's way over on the left-hand side, and they've squeezed it over on the NMR just to tell you there was something little hoodoo-y there as well. What that is, we don't really know. So this is going to give us a step in the right direction, so that way we know, are these really signals or not? And based on this information, no. Those are going to be super tiny, super small, and they are probably not major signals that I need to be concerned with. And that's very often the case, not every single time, but very often the case of what we see. All right. So where's that other kind of signal coming from? I mean, that is a proton, right? So yeah, we do have some protons. We've got a proton here, but that's not really on a carbon. It's on an oxygen. There is a chance that something like that will show up. It's going to be very weak. And that's probably where that third signal's coming from, that they're squeezing back onto the chart. But as far as the major signals that we're seeing in the main space of the NMR, it's coming from these 2 carbons ones that we've drawn here. Okay? All right, so now the next one is, let's take a look at splitting. So I know that we're going to get two signals here. I'm not really even interested in ranking right now. Let's just look at splitting. So if I look at this particular signal, whatever I get here, this is going to be a neighbor of 2. So 2 plus 1 is 3, and that means that we've got a triplet for that signal. So one of these signals better be a triplet. The next one, well, I have another signal that's here. Next door are no protons, and next to that one, we have 2 protons. So that's also going to be a triplet for that one as well. So for one of these compounds, I'm going to see a triplet for both signals. All right, so if I go to this one, I actually see a quartet and a doublet. That really doesn't match the predicted NMR spectra, does it? So that's probably not the NMR spectra for that one. If I look for B, well, this signal's a triplet, and that signal's a triplet. Ta-da! We did it! That's the NMR that matches what we've drawn. So this particular NMR is the carboxylic acid that has that group, C double bond OOH, and it had a C and a C, and it looked like that is the one that has the chlorine on the end, right? So if that's the one that has the chlorine on the end, I'll draw the chlorine there. This is a CH2 group, and that's a CH2 group. So there we go. So that matches pretty well. 2 major signals. That's what we're seeing very early on in the NMR, and each one of those signals will be a triplet. All right, now that means I hope that the other one is a pretty good match. So let's just double check it. We'll go here, we'll take a look at the multiplicity of it. So for this particular carbon, that one next door, that is a 1 kid group, and 1 plus 1 is a 2. So that means that I should have a doublet that is going to be with one of my signals. And then for this particular carbon, I've got 1 neighbor. That neighbor has 3 kids. 3 plus 1 is 4. So this is a quartet that I should have with another one of my signals. So let's just take a look and see if that matches. Here I get a signal, and that signal is a quartet. And then here I get another signal, and that signal is a doublet. So it does match basically the predicted order. So I'm going to get my carboxylic acid group, my carbon, and my carbon. So there we go. And then off of this is a chlorine, and we have a CH3 group and a CH group that is there. All right. The CH3 group, of course, is the one furthest away from the electronegative group, and that is going to be split into 2. It's a doublet. So that perfectly matches what we're seeing right here. It's the very first major signal, and it is split into 2. The next signal that I'm going to get is this CH group that has a chlorine on it. That is electronegative. It's going to happen much further downfield in the NMR, and it does. And that has a quartet that's assigned to it. And sure enough, that is that particular signal there. So it all matches pretty well. In this other one that we did actually first, we see 2 major signals. Which one's which? Well, it looks like this carbon is directly connected to that chlorine, and because that chlorine's electronegative and this one's directly connected to it, then that probably means that this one's going to be harder to flip. So this one is going to be a triplet, and that's probably going to match that one there. And then this one is more in the middle, right? It's further away from that chlorine. This carbon has a double bond O, but that carbon's not necessarily too electronegative. It's the oxygen that's more electronegative. So we're seeing not as strong of an electron puller around that area, and its electron cloud is a little more dense. So that one is also going to be a triplet, and that's probably due to that one right there. Okay, so we are matching signals, we're matching chemical shifts, we're talking about electron density, we're talking about electronegativity, we're talking about the term or idea of splitting the major signal into multiple parts, all in the name of NMR theory. All right, so I hope that I sounded really smart, because if I did, then you are too, because you're going along with this ride with me, and you should be able to explain things that way as as well. So use your words, use the terminology, use the organic language, and make yourself sound impressive. All right. So in this next video, we'll continue on with the splitting, and we'll talk about why this splitting even happened anyway, right? I mean, why is it going on? Are there more things that we have to be concerned with? What is the whole theory behind what's happening here? So that's what we'll pick up with in the next lecture video.